So we've departed from the Pico diagnostics platform where we did a simple relative compression check and we've identified a weak cylinder. Now I've left the vehicle in the same condition and we had around a 30% drop on a particular cylinder. So let's go back to the oscilloscope. We're still connected to the vehicle battery. So we're going to measure voltage, potential difference across the battery during compression, which is what the Pico diagnostics platform is using, because that was the only connection we had. I'm going to complement the voltage measurement with current, and you will notice that we've connected the second channel, the red channel, with a current clamp over the battery negative lead. I have deliberately set the polarity of this device so that the current appears to be taken out of the battery, something I feel quite passionate about, because I'm using this as consumption from the battery by the consumer, the starter motor. And of course, if the engine were to run, the alternator then would show a positive current flow, not a negative flow out of the battery. So, how are we going to set this up? 20 volts would be the most appropriate setting for channel A. Channel B, I'm going to choose 1 volt. Some of you will have seen me do this before. A very good simple reason. It's a very simple view of how to interpret current using voltage. The sensitivity or attenuation of the current clamp is every millivolt is 1 amp. There are 1,000 millivolts in 1 volt. So by setting 1 volt, I'm establishing a 0,000 amp range in both directions. When I conduct the test, you'll see that aesthetically it looks right, and the comparison of both voltage and current is much easier to understand. But we need a longer time base, so I'm going to set a 2-second time base, which gives us a sweep time across the screen of 20 seconds. Long enough for me to go and conduct the test. You can see the test running live. We'll come back and then do the analysis. Roughly a 10-second crank duration. Now, in terms of assessment, I've got quite a high sample rate, 10 millisamples, which gives me the opportunity, when I zoom in, dividing the amount of data that's stored in the buffer, which is how the display is acquisition, storage, display, the 3 functions of oscilloscope. We can extract the data out of the buffer with plenty of detail because I've got lots of data stored. So you get a very nice, accurate image. The noise on signal is due to the battery support, which I've kept to the vehicle because we do a lot of cranking tests. So I don't want to diminish the results of the test by a decaying battery. So I've supported the battery with a Fronius battery support tool. Now let me just explain my take on this current measurement. If we use a cursor and we measure the peak current draw, that's represented as 695 millivolts, which is 695 amps. It is that simple. Just move the decimal point 3 places. So I'm happy with that. I hope you are. However, what we do want to look at is the results of this test over a period when it's stable. So I'm going to choose. Now, of course, the last test we did looked at the voltage analysis, so let's take a look at that first. Voltage differential, and you can see there is a differential in voltage during the cranking process. And we can see the pattern, it isn't even. Now I find that a little difficult to establish. Good compressions would suggest that these are good compressions and these potentially are poor compressions. Okay, let's look at it from the current point of view. Now let's mark the good compression events. Obviously the negative events, these events, so I would say that we have 2 healthy compression events. That is a little lacking, and this is seriously lacking, so that is the problem event. So we're pulling during this stable cranking event, in other words, when the current's recovered, the engine's now revolving at around 250, 260 RPM. The amount of current consumption by the starter has recovered somewhat, and we're pulling just under 230 amps of current. However, this event here, which is obviously a weaker event, is only consuming, now we could also do a little bit of filtering here, guys, 198, let's call it 200 millivolts. So there's a 31 millivolt or 31 amp difference in the work rate on that cylinder. And you can see some cylinders are even worse than that. So that's how the relevant compression test is done, but you can do it using the scope in real time. Now, if we choose to filter, we might get a little bit more of an accurate assessment. Let's filter a little bit more. Let's see if we can improve this. Be careful with filtering, guys, because what we don't want to do, very high sample rates, a lot of noise in the signal. I don't want to filter out detail. So I'm going to hold at that point. I think my assessment is reasonably accurate. If we look at the performance between a good compression and a poor compression, it's 27 millivolts, 27 amps difference between the two, which is around 10% of the work rate done by the battery. So we can see there is a mechanical problem with this engine. Now, you may say, well, how do I know it's not a problem with the starter motor? Well, that's down to a different frequency. The rotation speed of the starter motor is much quicker than that of the engine, and the performance of the starter motor armature is represented in these events here with very high sample rates. So we can actually look at the performance of, if there was a problem with the windings in the starter motor, we're going to see there are some slight differences here of the current consumption from the starter motor, but not affecting compression, which are these events. So that's my take on a variation of the Pico diagnostic platform. We can do it, and I often do this test with the scope. I think it has a little bit more detail in it. We can measure the difference in terms of current draw from the starter motor with a poor compression. So that's the first basic test. I'm quite happy with the results of that test. I know there's a problem with the engine. Let's now try and develop a means of proving which cylinder the problem is on and potentially what that problem can be. Now, to do this, what I'm going to do is do a compression test while the engine's running. Now that means obviously that one cylinder will not have a spark plug in it. However, we're not really interested in the spark and the fueling. We're interested in the mechanical efficiency of the engine. So we're going to be doing a compression test with the WPS in cylinder 1 in real time, engine running, not cranking. You're going to see some very interesting results.